Hello students, in the last session we completed the concept of potential energy and then we did see what is meant by total energy, okay? So total energy actually means summation of potential and then the kinetic energy. You should have known that formula. Then finally we did see vertical circular motion of a bob, okay? So how is the potential energy, how is the energy getting stored in the bob at different instant during its circular motion, okay? So we did see those concepts, fine. So you should be clear with all those concepts that we have seen in the last session. So in this session we will do the concept of spring, okay? So that this will be kind of new stuff that we are going to see. So how is the force actually acting in a spring when you are about to stretch it or when you are about to compress it, okay? In what factor it is going to act, that's what we will see. So how is the spring force acting during the stretching and then the compression of the spring? So that concept will be done. Then we will see the energy that is getting stored in the spring, fine. So how is the potential energy that is about to store in the spring when you are about to stretch it or compress it, fine. So that part will be done. And then we will see the basic understanding behind the power. As I've already told you, it's a kind of energy divided by time, right? So we'll see that one. Then finally, to complete this chapter, we have like one more extra important big concept which is called as collision, okay? So the first part of the collision will be done in the session, so that will be like the completely inelastic collision, okay? So we will do that part in the session. So in this session we will do like three important concepts. The one is completely related towards the spring, and then we will see like what is meant by power, basic understanding and stuff that you need to know. Finally we will see the first part of the collision, which will be like the completely inelastic collision, fine. So those concepts will be dealt in this session. In the next session we will complete the entire collision part and all those stuff, and then finally we will see like some extra thing, mathematical stuff, which is like the some basic trigonometric functions which we need to know, right? So those stuff will be done in the next session. So in this session, as I've already told you, we will do like three important concepts. In that, the first one is like the spring, okay? Now let's see the concept behind the spring, okay? So here I've just drawn the diagram for the spring, okay? So here initially, if you look at this spring in the first situation over here, it should be pretty obvious. I've just put a mass on the one end of the spring and the other end of the spring is actually attached to a wall, okay? Which means the one end is immovable. So that will be a thrust with respect to the motion of this particular object, okay? Got it? So initial condition is like the unstretched condition for the spring, which means the spring is in neutral condition, which means there isn't going to be any push or pull in the first situation, okay? So that condition is actually unstretched situation, okay? So that will be the first initial position, okay? So this position is actually unstretched. Got it? Which means x will be equal to 0. So that's the starting position from which I'm just going to pull it to a distance of some x. Either it could be like the plus x, so that will be the stretched condition, or I could actually compress it, which will be like the negative x, okay? So here, obviously, when the spring is in neutral position, which means when it is at the x equals 0 position, which means I haven't stretched or compressed it, okay? So when it is in that state, obviously there wouldn't be any force that is getting acted between the spring, okay? So that's not going to be there. So in the initial situation, in the normal situation, which means in the beginning situation, you will have the spring force to be like 0, right? So that will be the first simple case, okay? So then what I'm going to do is I'm just going to stretch it to a certain distance x naught. Okay, so from the origin I'm just going to stretch it to a certain distance plus x naught, okay? I'm going to move towards the right side, okay? Then obviously in this situation it is going to get elongated, right? So the second case will be the stretched condition, so I'm just going to stretch it to a distance of plus x naught. That's going to happen. So this condition is actually stretched, okay? So here I'm just going to stretch it, so this condition is stretched to a distance of plus x naught from its origin, fine. So when I'm about to stretch it, what will happen to the spring is it is going to give a pull that is opposite to the direction of the stretching, okay? So here I'm just going to stretch it towards the plus x naught. Obviously from the intuition we know that spring should actually pull it inwards by the same amount of force. That is when the inward pull given by the spring and then the force that I gave for that particular block to pull it will also balance each other, okay? Therefore the spring force will act opposite to the direction of the pull that I gave to that particular block which got attached to the spring, okay? You should be clear with this notion. Therefore here the spring force will be exactly opposite to the direction of the pull that I gave over here. Therefore the spring force will act in the negative x-axis, right? Exactly opposite. Fine. So in the third scenario, here I have compressed the spring. Okay, then obviously the spring force should act opposite to the direction of the compression, which means it will act in the positive x-axis, right? Exactly the other way around that we have already known by intuition itself. Therefore, here I'm just going to compress it to a distance of minus x naught, which means the spring force will act towards the plus x direction. Okay, so here the spring force is going to act towards the plus x direction, right? So these two things will be opposite to each other, right? So when I'm about to compress it, it will actually push us away from compression. Okay, so those two forces will act opposite to each other. So when the push that I gave to this particular block and the spring force is going to balance each other, so that will be the mean position where it is going to be at rest. Okay, right? So this is how the spring force will act. So spring force will always act opposite to the direction of the pull that I gave. Okay, so if I'm just going to pull it, then it will push it inwards. I mean, if I'm just going to pull it outwards, then obviously it will pull it inwards. Okay, so those two things will be opposite to each other. That's how spring force will be related, right? So this is the notion that we need to know, right? So now I'm just going to give a generalized formula for the spring force, right? So the first thing that I have already known here is, if I'm going to pull it outwards, then it will pull it inwards. So these two stuff will be oppositely related. Therefore, I'm just going to introduce a new concept. Therefore, I'll have to put a negative sign over there, right? So spring force will always act opposite to the direction of the motion that I'm giving to that particular block. Okay, right? So you need a negative sign which is going to be placed over there. Then what we will have is, so it will act to certain limit, right? So first let us put it this way. If I'm just going to give a force, if I'm just going to give a pull of 1 Newton to that particular spring, what will happen to the spring? If I just give a pull of 1 Newton to that spring, what will happen is it will get stretched a little bit, and then the inward pull given by the spring and the pull that I gave will balance each other. Therefore, this will be at an equilibrium position, right? So then if I just give like extra pull to it, which means a force of 2 Newton to that particular spring, what will happen to that spring? That spring will stretch a little bit extra, and then it will come to the neutral position, and then it will come to the equilibrium position, which means that will be the point where the inward pull given by the spring and the pull given by me will get balanced. Okay, so from this intuition it should be pretty clear that more the displacement you're just going to produce with respect to the spring, obviously the spring force that is going to act inwards will keep on increasing, right? So more I'm just going to elongate it, then obviously the spring force will also be greater, right? Fine. So same analogous situation will happen in the case of compression, right? So the more I compress it, the more it will actually push me away from the compression. Okay, so these two things will act opposite to each other, proportional to that of the displacement. Okay, so the more the displacement, you're just going to make the elongation, then in that situation more the spring force that will get generated between the spring, right? So the idea and the notion should be clear, right? If it is like 1 Newton, then it will stretch by a factor of 1 centimeter, problem a kind of situation. Then if I just give like 2 Newton force to it, then it will get stretched a little bit extra. Let me assume it to be like 2 centimeter. Okay, so if it was like 3 Newton, then it will stretch to like 3 centimeter. Every single situation it will not actually increase proportionally. There will be certain limit up to which it will increase proportionally. Then depending on the nature of the material and all those other stuff, that's going to vary. But for a generalized overall situation, it is pretty obvious. More the elongation, more the inward pull, which means the spring force will act opposite. Also same way it will act more when the elongation is more, right? Therefore those two things should also be related, right? So when I'm going to give the direction of the spring force, that was actually negative. Same way it also depends on the elongation, which means it is also dependent on this x that I'm going to move, right? Therefore spring force Fs will be equal to negative of kx, right? So k will be the constant, k or kappa, whatever it is. So k will be the spring constant in the situation, and then x will be the displacement what I have produced to that particular spring, right? It's not always linear, but in the generalized overall situation, I'll be able to make it as a linear stuff. Okay, so depending on that particular scenario and the design of the spring, this term is going to vary. But when they are just going to give you spring in a simpler fashion, then it is pretty obvious. It just directly depends on the extra expansion of the compression that I have produced with the case of the spring. Okay, so that should be clear. So here minus kx, where k is nothing but the spring constant in the situation. Okay, so spring constant will be like the k. Got it? You shouldn't have any doubt in this part that I've discussed over here, right? Next, let us see the graph for this particular equation. So here, if I'm just going to draw the graph for this equation, obviously this equation is a linear equation, right? So you do not have any powers here. The power is equal to 1, right? Therefore, it should be a linear equation. That's obvious. As usual, here you have got the y-axis to be like Fs, spring force, and then the x-axis to be like the displacement x, right? So that is straight away matched. And then if you look at this sign, it is like negative, which means that linear straight line should have a slope of negative. Okay, we should have negative slope, which means the line should be between the second quadrant and then the fourth quadrant. Okay, because you are going to have a slope that's going to be negative, right? So it should be clear. Same way, if I'm just going to give you an understanding with respect to the graph, it will be such that when you move, when you actually compress it, which means when you move the spring towards the negative x-axis, obviously the spring force will be positive, right? So it will be linear with respect to the second quadrant. Same way here, when you are about to move the spring, which means towards the plus x-axis, that's a kind of expansion situation. In that situation, spring force will act towards the negative direction, right? So those two things will be oppositely related, as I've already told you. Therefore here it should be a straight line of negative slope, so it will look something like something of this sort, right? So that will be a negative slope, right? So this is actually a straight line, right? It should be clear. So this is what we need to know regarding the spring force and all those stuff. Now let us see how does the work actually get stored in the spring, right? Obviously the energy will get stored in the spring in the form of potential, right? So whenever the energy is going to get stored, we'll call it as potential, because we have to make that energy storage a positive thing, right? Okay, so here the construction is just the same thing that we have discussed earlier. So the spring, when it was when it was in that unstretched situation, so when it was at its mean position, in that situation there wouldn't be any energy stored into it, right? So that will be the unstretched case where everything will be like in the main position, which means you wouldn't have any energy stored into it, right? Next, what I'm going to do is I'm just going to pull it to a certain distance x. So the initial distance will be like x equals 0. So that will be the initial distance, which will be like x equals 0. Then I'm just going to pull it to a distance of x. Okay, so that will be the final position. Okay, x or x naught, whatever it is. So depending on the pull, I'll be able to plug in. Okay, if it was like 1 meter, then I'll just plug in 1 into it. If it was like 2 meters, I'll just plug in 2 into this particular x, right? So depending on the pull, the energy will get stored into it, right? So that stuff should be obvious. If it was like if the force was like constant, then there isn't any problem of integrating it. Just do the force times the x will give you the answer straight away of the energy stored into it. But in this situation, the spring force in and itself is variable, right? F is in constant. More the elongation you make to the spring, more the spring force that will act in the spring, right? Therefore, F is also increasing with respect to the x. Okay, so Fs is in constant. Therefore, I'll have to do the integration with respect to every single position, because force in and itself is variable in this case, right? The logic should be clear. Okay, so here x equals 0, that was the initial position. Then I pulled it to a distance of x, that was the final position. The spring force isn't constant, it is also increasing with respect to the x, right? Therefore, I'll have to do the integration to get the final answer. Okay, so integration will be done as usual. So the small element will be taken and then I'll have to integrate it over the complete distance, which means between 0 to the x, right? So here, to get the work done, I mean to get the potential, that will be equal to the negative of the work done, right? So that will be the logic, right? So work done. So for the case of work done, I'll substitute the work negative of vector F dot. So I'll let, if it was like a three-dimensional motion, then I'll substitute like dr. Okay, so dr actually means the small element in that particular direction, right? So here the direction is obviously along the x-axis, therefore I do not want to put like dr and things of that sort. Here I'm just going to pull it in the x direction itself, therefore that finite small element, that small element will be like dx, right? Therefore here vector f dot vector dx. Okay, this should be clear, right? First let us remove the dot product from it, and then I'll also, if I have to remove this dot product from it, then obviously dot product of two vectors will be a scalar, then obviously these two vectors will also be removed. Okay, so if we have to remove this dot product, then I'll do the integration. Okay, so to remove this dot product, I'll have to find the theta between vector f and then the dx. Okay, displacement. Here in this situation, obviously the force was acting along the negative direction, right? The spring force was acting along the negative direction. Yeah, this will be the direction of the spring force, and the x dx was along the positive direction. Okay, so those two things were opposite to each other, as we have already told. Okay, that is why you have got this negative sign, right? But in this situation, I'm just going to make it a scalar initially itself. Therefore, I do not want to plug this negative sign while we are going to substitute kx. Okay, so that wouldn't come into picture. So here it was a spring force, right? So spring force was actually opposite to the direction of the pull that I gave it to it. Therefore, the angle between those two vectors fs and dx will be equal to 180 degree, as these two things are opposite to each other, right? Therefore, cosine 180 degree will be equal to -1. Okay, so that should be pretty obvious, right? So here to get the theta, it is obviously like 180 degree. So you'll have like negative integral of fs. Okay, let us put it this way, modulus of fs. Okay, and then modulus of dx. Okay, and then you'll have like the cosine theta. So here the theta will be equal to 180 degree. So here the theta will be equal to 180 degree, which means that's going to be like -1, right? So obviously this -1 and then this negative, it will become positive, which means it is clear that the energy got stored into the system, right? So whenever the energy got stored into the system, the potential energy will be like positive, right? Right? Initially, to get the potential energy, I just plugged in the negative sign, and then I just got one more negative sign because those two vectors were actually opposite to each other, right? So if that was the case, then it should be pretty obvious the energy has to be stored into the system, right? Therefore, these two negative will become positive, right? Then instead of fs, I'll have to substitute kx. Okay, you shouldn't put the negative sign. It should be clear because I've already taken the modulus out of it, which means I'll just have to substitute the only the magnitude into it. Okay, so only the value that does matter. The sign doesn't matter. We have already tallied that sign in this case. Okay, so let me do the math thing into it. You'll get the answers right away. So here you will have kx. Okay, so then you will have like dx. Got it? I have just removed the dot product and all those stuff from it. So you have got like kx dx. Okay, so now I'm just ready to integrate it, which means from the limit 0. So that's the starting position, obviously, and then I've stretched it to a distance of x. Okay, the x could be whatever variable depending on the situation. So the final position will be the x. Okay, now let me do the integration. So if I do the integration, you will have k, that's going to be constant, right? So let me write it outside the bracket. So I'll have k, and then x dx will be like something of this sort, x squared by 2, and the limit will be between 0 to x. Okay, so that's the limit up to which I'll have to do the integration. So if I do plug in the upper limit minus the lower limit, you'll have k x squared divided by the 2. Okay, you wouldn't have any second limit to apply, which means lower limit to apply, because obviously that will go to 0, right? So the energy that got stored into the spring will be equal to u, that will be half kx squared. Got it? So the energy that got stored in the spring was equal to half kx squared. So this term will be positive, right? So you'll have to note one more thing into it. If I just substitute like plus x into it, if I'm just going to elongate it, in that situation the energy will get stored because it is positive. Same way, even if I compress it, I know the energy is going to get stored because once I release it, it will start oscillating, right? Therefore, if I just plug in like negative x into it, still it will become, still I'm going to square it, therefore it will become positive, right? Okay, so it doesn't matter whether you're going to elongate it, whether you are going to stretch it, or you are going to compress it, whatever the situation it could be, you will always have the energy to be stored, right? So that's the notion that you need to know over here. Fine, so next we will see one more graph into it. Okay, so that graph will give you the relation between the total energy with respect to kinetic and potential energy. Okay, so here I'm just accounting all those energies. Okay, so energy is just getting transferred in two forms. One is between the potential energy, and then the other one will be the kinetic energy. Okay, there will be sound produced. Okay, I shouldn't account that energy because that will get dissipated. Okay, I'm just going to idealize here. Fine. So there could be some friction loss between the block and then the surface, that also isn't going to get counted. Okay, but in the real time situation, I know if I'm just going to pull a spring and then release it, obviously at some point it will get dampened and then it will just come to its mean position. So that's not going to be the case over here. This is idealized situation. Okay, so that's what we are studying, right? So if it was an idealized situation, then obviously total energy has to be conserved, which means the summation of kinetic and potential has to give you always the same answer. That's going to be the total energy, right? Okay, so first I've drawn a graph over here for the potential energy, which means, so that will be obviously U equals half kx squared. That's going to be a parabola which is like open upwards, right? So here that's going to be, that's like total energy E, and then x naught, it is parabola open upwards, right? So obviously this is like the total, I mean potential energy. Okay, let me give you an understanding of this particular graph. So here, when the spring is in unstretched situation, when it is at like x equals 0, in that case obviously the potential energy will be 0, right? So I'm just going to stretch a spring to a certain extent and then I'm just going to release it. Okay, when I release it, when I have stretched it to the maximum extent, that will be the maximum potential energy stored. So that will be the plus x naught, right? Once I release it, all those potential energy will get converted into kinetic energy, right? So there will come a point where, which will be its mean position. That will be like x equals 0. That will be the position when all the potential energy that got stored because of the spring will get lost. Okay, which means the spring will come to its mean position, right? Then because of the kinetic energy, because once I release it, obviously the block will store the energy in the form of kinetic energy, right? So that kinetic energy will compress the spring once again. So once it's going to compress the spring again, it will move to a distance of negative x naught. So that will be the position when all the kinetic energy will get stored in the spring in the form of potential energy because of the compression. Okay, so then what will happen to the spring? Then again that compression will get relieved and and kinetic energy will get stored into that block and then it will be pushed away because of that compression. Okay, so that thing will keep on repeating and there will be an oscillation. So once all those energy gets lost to its surrounding, that will be the point when it will come to its mean position, right? So this motion will keep on repeating. So this motion is actually an oscillation which we will study in the later part of this physics 11th standard. As if now what we need to know is, so the energy will keep on changing between kinetic and then the potential energy because of that, okay, spring force that got generated, right? While I was stretching it, right? So this is the notion that you need to know, right? You shouldn't have any doubt in this part. So now I'm just ready to draw the graph for the kinetic energy. Okay, so it should be obvious. When potential energy became 0, the total energy should always be constant, right? When the potential energy becomes 0, the kinetic energy has to be maximum, right? When the potential energy is decreasing, the kinetic energy has to increase, right? Same way in the situation, when the potential energy is about to increase, the kinetic energy has to decrease, fine? So these two things has to get oppositely related, which means if this was a graph of parabola open upwards, obviously the graph with respect to the kinetic energy will look something like this, parabola open downwards. Okay, so those two things will be oppositely related, exactly, right? So the kinetic energy will be maximum when the object has reached the mean position, right? So that's going to be maximum. Then the kinetic energy will decrease. Okay, so that will be a graph of parabola open downwards, something like this. Okay, so this is how it's going to be. So let me take a random position. Got it? So let us take it in this fashion. So here I'll just take a position. So here the potential energy will be this one, right? So this will be the potential energy, right? Same way the kinetic energy will be this part. So this will be, this total distance will be the kinetic energy, right? So this will be the kinetic energy. Got it? Then obviously this u has to add up to this kinetic energy to give me the total energy. Okay, so if this was the kinetic energy, then this small portion will be equal to this portion. Okay, that idea should be clear. Therefore here this portion will be equal to E. because when I'm going to add these two things, which means kinetic energy at this position was equal to this point, same way this leftover, this will be the potential energy, right? So this distance and this distance has to be same. That is when if I just add kinetic and potential, I'll end up getting the total energy. Okay, the logic should be clear. So whatever energy that the spring has lost will get stored into that particular block in the form of kinetic energy. Okay, so that's the idea that I'm aiming for you to understand. Okay, that's the notion that you need to understand. Okay, so here it was able to reach certain maximum, it was able to gain that kinetic energy. So whatever kinetic energy that it has gained, that will be lost by the spring. Okay, so whatever energy that the spring has lost in the form of potential energy, that same amount of energy will be stored into that block in the form of kinetic energy. Okay, so obviously if this was a parabola that was open upward, then the kinetic energy will be a parabola that's going to be like open downwards. Okay, so we will see this particular graph much more exhaustively in the chapter of oscillation. So that will be in the 11th volume 2 part. As if now what you need to know is these two graphs will be like oppositely related. So whatever kinetic energy that has lost will be stored in the form of potential into the spring. Other way around is also true, right? So that's the idea that you need to know, because the total energy will get conserved. There isn't going to be any other loss to the surrounding or anything else. Therefore, total energy will be equal to the kinetic and then the potential. So that will be equal to E, which is equal to kinetic plus the potential K plus U, right? So this is what that you need to know regarding this particular graph. Okay. So next we have got the concept of power. Fine. So we'll have to discuss what is meant by power. See, this is something that we have already told in the beginning of the chapter itself. Energy and work, those two parameters are the same thing. Okay. But when you consider power, it simply means what was the energy that got consumed in that particular time, in the given time. Okay. Which means I'll have to divide it with respect to that time. So the energy consumed per unit time will give you the power. Got it? So here power is nothing but the energy consumed per unit time. So that unit time with respect to SI standard will be the seconds. Got it? So it will be like the power. So the total energy consumed divided by that particular time. That will give you the energy consumed per unit time. So it's like del W divided by del T. Okay. So work and energy both are the same thing. But the power is nothing but I'll have to divide it with respect to that complete time, which will give me the energy consumed per unit time, right? You should be clear by this with this logic. Then the unit of the power is actually watt. Okay. So we have named this power with Watt because to honor a scientist who is actually James Watt. Okay, he was a scientist who worked on steam engine and those stuff, right? To honor his name, we have just to honor him, we have just named the unit for power as Watt. Okay, so the other unit will be del W divided by del T. Therefore, it will be like joule per second, right? So the next unit will be like joule per second. For work it will be like joule, and then for time that's going to be like second, right? So let me do the dimension for this particular power. Okay, so the dimension will be like joule, which means work, that's going to be like force times the displacement, right? So I'll have to split the force is nothing but the mass times the acceleration, right? So to get the mass you will have, so for the mass it will be like kg, mass times the acceleration will be like meter per second square. Okay, so that will give you the force. So this particular term will give you the force. Work is nothing but the force times displacement. Therefore I have to multiply one more meter into it for the displacement. So that will give you the next total. I mean that will give you the unit for the joules. Then for the second, that's going to be the second straight away. So divided by the second, so that will be like S inverse. Got it? So the dimension for the power will be, instead of kg you will have like mass, that will be like m, and then you have got like 2 meters, right? Meter square, that will be like L square, and then the final term will be S power minus 3, which will be like T power minus 3. Got it? So this is the dimension for the power. Okay, so this is obvious and easy, right? So once you are thorough with the formula and the understanding behind the formula, it will be easy for us to get the dimension for that particular term. Okay, so That's the reason why I didn't teach you more related to the formula in the first chapter, units and dimension chapter. Okay, as we keep on progressing with other chapters, it'll obviously all those formulas will become easy to you, right? So once you're thorough with this particular with those formulas, obviously straight away this dimension will just come out, right? So only thing is you should know the formula. So to get the formula, the idea and understanding has to be clear. Once that part is done, obviously dimension will just be any piece of cake. Okay, it will just fall down easily, right? So this is the understanding that you need to know regarding the power. Then I've just given you a simple thing over here for much more clear understanding. So you have got a bulb over here, and then that bulb is going to emit 600 joules of energy in 10 seconds. Okay, so it is consuming 600 joule of electrical energy to produce this light, right? So 600 joule in 10 seconds. What they're asking us is what will be the power of this particular bulb. So obviously the total energy that it released divided by the time, that will give us the power that it is consuming from the electrical energy, right? Therefore power will be equal to del W divided by del T, right? If that was the case, here it should be like 600 divided by 10, so which will be equal to 60 watt or 60 joule per second, which means it is consuming 60 joules of energy in every single second. Got it? So therefore the power of this particular bulb is like 60 watt. Fine, this one should be clear. Then there is this thing, 1 horsepower will be equal to 746 watt. Okay, so generally in olden days, in 1800s, 1700s, when they were actually designing steam engines, fine, so James Watt was the one who just developed a steam engine, okay, based on those ideas. When we are about to give a presentation to the people, okay, so we will have to compare our engine with respect to the horse. Okay, so in those days, horse were actually used for the mechanical work jobs. Okay, for transportation and all those stuff, horse were used. So when we have to compare between the motor and then the horse, this was the conversion that they actually used, right? If your motor is able to produce 746 watts of energy per second, then that will be equal to 1 horsepower. Okay, so for the basic understanding for the common people, this was the relation that they were actually using, which means 1 horsepower that will be equal to 746 watts. So this is not an SI unit, this is just an relation that if you remember, it is good. That's it, finished, right? Okay, so these are the understanding that you need to know regarding the power. So power is just a simple one. What was the energy that got consumed in 1 second? That will be equal to the power, right? So you should be clear with this notion. Same way you should be clear with the idea of the spring that we discussed earlier, right? So we are into the last part of the session, which will be the collision, right? I mean, before that stuff, we have got one more thing which is left. That will be like unit. So 1 unit, that will be equal to 1 kilowatt hour. Okay, so when a EB guy comes to your home, he will get the reading from the EB meter, right? So he'll tell you that you have consumed 400 units of energy or else 500 depending on the situation, right? So when he tells you, he's going to tell you just 500 units, 600 units. So that's an easy convention for the common people. But how should I actually relate it with respect to joule per second? That's what we are going to see over here. So 1 unit will be equal to 1 kilowatt hour. Okay, so now I'm just going to expand it with numbers for these particular terms. Okay, so 1 kilowatt hour, which means 1 will be like 1, so that's straight away. Kilo means that will be like 1000, right? So that will be like 10 power 3. Instead of watt, I'll just plug in joule per second. Okay, 1 joule per second. For hour, obviously the SI unit is second, therefore I'll convert the hour to second. Okay, so that will be 60 into 60, right? Or 3600. So that's going to be like 3600 seconds. Fine. So if I just do the multiplication, I'll get the 1 unit, which will be second and second will get cancelled out, right? So second and second will get cancelled out. If I do the multiplication, I'll end up getting 3.6 into 10 power 3. 3.6 into 10 power 3. Okay, joule. So here, when I look at the unit, it is obvious this is joule. Fine. So unit actually is a measure of energy, not the measure of power. Okay. So here, what is actually the measure of power joule per second? I did multiply it with R, another 1 unit. Therefore, another 1 unit of time. Okay, therefore this 1 unit will be equal to the energy that got consumed. Fine. If they tell you like 400 units of energy that got consumed, which means I'll have to multiply this term by 400. That will give me that much amount of energy in terms of joule. Okay, so 1 unit actually equal to 3.6 million joules. Okay, so million, right? So 10 power 5 will be like 1 lakh, therefore 10 power 6 will be like million. So here if I just consume like 3.6 million joules of energy, that will be equal to the 1 unit of energy that got consumed, right? So that's the relation between 1 unit, which is the common EB unit that we get, and then with respect to the SI unit with respect to joule. Okay, so this is the relation between those two stuff which we need to know, right? So it should be clear, right? There shouldn't be any doubt in this part. Then we will see the final part of the session, which will be the collision. Okay, in collision I have got three different types. Okay, the first one is like completely inelastic collision, right? So the name itself clearly suggests it is inelastic, which means none of the deformation has regained its original shape. Okay, so the deformation is there. Okay, so that's the first thing, which means completely inelastic. So you are going to have a permanent damage between those two surfaces. So that's completely inelastic. So there isn't regaining of its original shapes. That's not going to happen. So that is why it is called as completely inelastic collision, right? So that's the first type. The next one will be the common case, which will be like inelastic collision. So this will be like the common one. So that will be like inelastic collision, and the final one will be the elastic collision, right? So we will see derivation for completely inelastic collision and then for elastic collision. So these two are two different extremes and idealized situation. Okay, so the first one is like inelastic, which means there is going to be permanent deformation into it. So the example for completely inelastic collision is a kind of this situation where you're just going to fire a bullet against a wooden block. Okay, so the wooden block is thick enough to completely hold the bullet into that block. Okay, so when I just going to fire the bullet into that particular block, so the bullet is going to pierce through that block and then the bullet will get stuck into the block. Okay, so then what happens is both the bullet and then the block is going to travel with certain constant velocity. Okay, so that condition is completely inelastic collision, right? I'll have to idealize the situation, which means there wasn't any energy loss to the surrounding in the form of sound or all those stuff. Okay, so I'll have to idealize it. If that's the case, in that situation, obviously I know the bullet will get deformed from its original shape. Same way, the block would be pierced through, therefore you are going to have a hole in that particular block. It is not going to regain its original shape, which means that's the situation where it is going to be completely inelastic. Okay, so that's the first condition. So it is pretty obvious in that situation I didn't regain the original form, therefore you are going to have a maximum kinetic energy loss in that situation, right? So that's the first situation where you will have maximum kinetic energy loss, right? So in the first case you will have maximum kinetic energy that will get wasted. Okay, so you will have maximum kinetic energy is wasted. Okay, so that's the first case, right? Now let us see the third case. Obviously inelastic collision is just the in-between case which will happen all the time, right? So that will be the in-between case. Okay, with the case of elastic collision, this is a kind of perfect situation. This is a kind of ideal situation. So here also in this situation there wasn't any other loss to the surrounding. Okay, so two things got collided and regained its original shape and then it bounced back. Okay, so that's going to be elastic collision. So the example, so some closer example to this elastic collision will be throwing a ball against a wall. Okay, so the wall is fixed and it is rigid. Okay, the situation is idealized, which means there wasn't any energy loss to the surrounding in the form of sound energy or things of other heat energy or whatever it is. Okay, so when a ball is going to hit the wall, there shouldn't be any heat produced between the ball and the wall. Okay, if that was the case, what will happen to the ball? The ball will get squeezed into the block or the wall, then it will just get bounced back, regaining its original shape, right? So if that's the case, with whatever velocity I threw on the wall, see, with same velocity and same energy, it will get bounced back to the hand. Okay, in the real situation that's not going to be the case. You will have some energy loss, right? So that in between situation will be the inelastic collision. Okay, so elastic collision is a perfectly idealized situation where you will have all the kinetic energy that will get conserved. Okay, so the third case will be like kinetic energy is conserved, which means there isn't going to be any loss from the kinetic energy in its velocity. Okay, so kinetic energy is conserved, which will be the third case. Fine. So these are the three situations that you need to know. So we will see derivation with respect to completely inelastic collision that is possible. So with respect to inelastic collision, that's not possible because that's an in-between situation. Okay. So that's a kind of intermediary case. Okay. So depending on the nature of the substance and surrounding and all those factors will come into picture, and then I'll be able to get the final velocity. Okay. So that's a for that particular case, I'll have to know every single parameter that is getting involved, okay, which is not possible. Therefore, inelastic collision, I'll not do any derivation related to inelastic collision, okay. So that's a kind of intermediary situation. So let me write it this way. That's a kind of in-between situation, okay. So then for the third one, which is like elastic collision, that's the case, that's a perfect case, okay, perfect idealized situation where the complete kinetic energy will be conserved, right? So the formula, I mean, for the derivation for the elastic collision will be done in the next session. So in this session, we will only see completely inelastic collision, and then we will see some derivation into it, okay. So I have already made it clear. So completely inelastic collision means you're just going to hit a bullet against a wooden block, and the bullet will get trapped into that particular block, and both those blocks are going to travel with certain velocity. So that's the case of completely inelastic collision, right? So let me do the same thing over here. So here I have just drawn a picture over here. This is a case before the collision, okay. So you are going to have two masses. Let us make this situation simple. So the final velocity of the second block will be 0, okay, a kind of block that is at rest, okay. So u2 will be 0. So u will be the initial velocities, v will be the final velocity as usual, right? That's the convention that I'll stick to, okay. So u will be the initial velocity, v will be the final velocity. u2 means the velocity of the second mass, okay. So the velocity of the second mass initially was equal to 0, and then you had some velocity for the first mass that will be like u1, okay. You had certain velocity, obviously these two has to collide, then this should have velocity along the plus x direction, right? If it was like negative x direction and the object was on the other side, obviously you'll have to plug in negative sign because we will do the momentum conservation. So whenever we are doing momentum conservation, obviously the sign has to be involved, right? So that's an vector stuff. Initial momentum will be equal to the final momentum because we just got that understanding from the third law, Newton's third law, which you have seen in the last chapter itself, right? We did solve multiple sums that were related to the momentum conservation, explosion sum, and all those stuff, right? So even in this situation, I'll use the momentum conservation because we know only those two objects interacted. Rest all other consideration isn't considered because this is a kind of idealized situation, right? Okay. So then after collision, what will happen? So these two things will get stuck to each other, and then it will start moving with certain constant velocity, right? So in the final situation, these two mass will just move with a constant velocity v. That's what it's going to happen over here, right? So this understanding should be clear. You shouldn't have any doubt in this part. Then we will do the momentum conservation. So the momentum conservation is simple. The initial momentum will be equal to the final momentum, okay. So we have discussed this concept exhaustively in the last chapter itself. It should be clear. So here the initial momentum will be equal to that of the final momentum. So those two stuff you will have to put plug-in vectors over there, okay. Now let me do now let me plug in the initial and then the final momentum. Initial momentum will be like m1 u1, okay. For the first mass it will be like m1 u1, and then for the second mass that's obviously going to be 0, okay, because u2 is 0. The term will go to 0, which will be equal to the final momentum, which will be equal to m1 plus m2, because those two masses gets combined, and then it is going to travel with the some constant velocity, which will be like v, okay. So that's the final velocity, right? So that's the diagram that I've drawn over here, right? Here if it got split, then it will be like v1 and v2, but in this case those two masses got combined, and then it is traveling with certain constant velocity v, right? So this thing should be clear. Therefore v will be equal to the final velocity of the combined mass will be equal to, just do the rearrangement, you'll get the answer. So that will be equal to m1 divided by m1 plus m2, and then multiply it with u1, okay. So this will give you the final velocity of the combined mass, right? So I have already told you in this situation we will have like maximum kinetic energy lost, okay. So to get the kinetic energy loss, I'll have to subtract obviously the initial kinetic energy from the final kinetic energy, right? So let us find out how far the energy will be lost in this case, okay? So it will be something like this. Initial kinetic energy will be the greater one minus the final kinetic energy, okay? So obviously, initially the kinetic energy will be greater when compared to the final kinetic energy. Therefore, this term has to be positive, right? So when I do the solving step and ended up getting the del k loss, this particular term has to be positive, right? So once I do it, I'll get it. This term will be positive. Let's verify at the end, okay? So here I'll have to subtract kinetic and initial kinetic energy from the final kinetic energy. Let's see what is the initial kinetic energy. Initial kinetic energy will be something this one, right? Half m1 u1 square, right? Because the mass m2, it didn't have any velocity into it, therefore u2 was equal to 0, right? So that term isn't going to come over here. So this one will be the initial kinetic energy, and obviously the final kinetic energy will be the combined mass, right? So negative of the final kinetic energy, which will be like half, right? The combined mass, which will be like m1 plus m2, and then the final velocity, which will be like the v square, right? I just found out this final velocity from the momentum conservation, right? So let us substitute that one straight into it. You will end up getting ki minus kf, okay? So the next step will be half m1 u1 square minus half m1 plus m2, okay? So this is one single term, and then v square. So instead of v square, I'll substitute m1 square divided by m1 plus m2 the whole square, and then you will have u1 square, okay? So if I do cancel out these two stuff, m1 plus m2, and then one more m1 plus m2 in the denominator, let me do the solving. I'll get the answers right away, okay? Fine. So let me factor out half m1 u1 square. So if I factor out this one, you'll have half, okay, m1 u1 square, that will get factored out from the first term. So you'll have like 1 minus, if you just look at this entire term, you'll have like half will get factored out, and then you'll have like 1 m1 which will get factored out u1 square, right? So the leftover will be this one. You'll have like 1 m1 in the numerator, and then you'll have like one more m1 plus m2 in the denominator, right? Now just do the cross multiplication, you'll end up getting the answer, right? So we'll have to do the cross multiplication over here, right? So if I do the cross multiplication, you will have half m1 u1 square, then you'll have like m1 plus m2 minus m1 divided by m1 plus m2, okay? This should be clear. Now this is like plus m1 minus m1, those two things will get cancelled out. So now I've just got the del k loss, which will be equal to half m1 u1 square, so m1 m2, so those two things will come out, right? So you are just going to have one more m2 in the numerator, so you'll have like m1 m2 u1 square divided by m1 plus m2, right? Okay, so this will be the maximum kinetic energy lost while you are having completely inelastic collision. So that's the worst case. So if there is going to be two collision and none of the deformation regained its original form, okay? So if that was the case, then this will be the maximum kinetic energy lost in that particular collision. Fine. So that's the completely inelastic collision, right? So del k loss, this thing has to be positive, right? Let us verify it. It's like half m1 and m1 and then m2. These two terms can never be negative. Obviously that's going to be positive. Multiplication of those two terms will be positive, and then addition of these two terms will also be positive. When you just look at u1 square, it doesn't matter whether it is in the positive direction or the motion is in negative direction. I'm just going to square it. Therefore that term will also become positive, right? So when you look at this entire stuff, it is pretty obvious that the kinetic energy has been lost, and then it is also positive. So this is the maximum kinetic energy that has been lost when you have like collision between two different objects, okay? So this is the worst case scenario, right? So in the next session we will see like elastic collision. That will be the best scenario, okay? So in that situation, the complete kinetic energy will get conserved, right? So that's a kind of situation where I'm going to throw a ball against a wall, okay? So we'll see that one in the next session, okay? So you should be clear with all the concepts that we have discussed in this session. So we did see the entire concept that are related to spring. Okay, how is the force that is getting involved in the spring that was dealt, then how does the energy that is going to get stored in the spring, that too was done. Then we did see what is meant by power. Okay, so power is nothing but the energy divided by the time, and we did see some basic understanding behind the power. It has to be clear. Finally, in this session we saw like collision. So there were like three different types of collision. In that we are just going to study two different collision, so the first one and then the third one. So in this session we completed completely inelastic collision, right? So in the next session we will do like completely elastic collision, and then we will do some extra part which is like coefficient of restitution, and then some basic trigonometric collision that we have to know, right? So with this the video gets completed. Bye.